In this video, we will develop a 2D model in Python for predicting diffusion and reaction. The basic idea is that we have a well or a tank like this, and in the bottom we had some contaminated water or wastewater that release hydrogen sulfide. So we always have a constant concentration of hydrogen sulfide in the bottom. This is a Dirichlet boundary condition. In the top of the tank, we have a release of hydrogen sulfide by convection with the bulk air phase. So this is a Robin boundary condition. So this is along the z-axis. In the middle of the tank, we can kind of split the tank in two pieces with a central line here, a symmetry axis, because we assume that what's going on from position 0 to the radius of the tank is the same in all angles around the tank. Therefore, we will not be concerned with this part of the reactor in this example. Because we have symmetry in the middle of the reactor, we can assume that we have a Neumann boundary condition at the center. This is because if we have some concentration that is completely mirrored on both sides, we will exactly have a gradient of 0 in the middle of the tank. Therefore, we have dc dr is equal to 0 at the center. On the right side, we will now assume that we have a biofilm that consumes H2S on the surface. So we will have a balance between the flux and the reaction rate at the right boundary. So this would be a Robin boundary condition. Now let's get back to Spider. All right, so I have already defined the diffusion coefficient for hydrogen sulfide. We will assume that the height of the tank is 5 meters tall and the radius is 2.5 meters. Because we have two dimensions now, we need to define space step sizes in the radial dimension, and we put this to 0.1 meter, and in the z dimension, which is 0.25. We will then make grids for both the z and r dimensions. Like this. On the side of the reactor we have the biofilm, and we will for now just assume some first order reaction to not make it too complicated. And we will have a rate constant on the surface of 0.0005. And that will end up having units of meter per second. In the top of the reactor we have the mass transfer coefficient Ka. We will set it to this. That will also have units of meter per second. Then we will, for our own intuition later, we will make nr, which is the length of the grid, and nz. This will come in handy later and corresponds to the number of nodes in each dimension. Then we will define the state variable, the concentration, and we will give it a shape that corresponds to the dimensions, to the length number of nodes in each dimension. So that would be nz point nr. And at the index 0, in the Z dimension, and at all R nodes we will have an initial concentration of 1000 ppm of hydrogen sulfide. And because we will pass this state variable into the solve IVP later, we need to flatten it so it has only one dimension. So right now it is a two-dimensional array of nz times nr, but we need to flatten it, and we can use a function called or a method called flatten, and we will make the variable here. So this is a method, and we need to put order equals to false. So this means that we are stacking all the columns on top of each other. If we didn't have this order equals F, then it would stack it row wise, so stacking all the rows, but we don't want that. We will make our rates function now. We know that we will put something called C flat into this one, but we'll come to that later. So the first thing that goes into the rates function, we have to reshape the size of C flat in order to understand more intuitively what to do with it inside rates. So we make a 2D array again from the flat C flat array, and we can do this by using the function reshape, and we reshape it to these dimensions. Again, we will use the argument order flat. Now we will make the derivatives, and because we have a two-dimensional state variable, we also make a two-dimensional derivative array, and we can use the np zeros, but then use the like function here, which creates the dc/dt in the same shape as the input we give here. Then we will make the number of indices, so ni will be corresponding to the last index in the z direction, and that would be equal to z minus 1. And we will make one called nj as well, which will be for the radial dimension. And now we will start to define the boundary conditions. So the easy one is the lower in the bottom, where we have a Dirichlet boundary condition. And this is a Dirichlet boundary condition. And here we have that all C at Z equal to 0, and for all R is equal to 1000 ppm. So therefore, this is exactly what we have for the initial condition in that position. So we just set the derivative in this position to 0. So that would be at Z position 0, and for all R we set it to 0. So I'm just being explicit about this boundary condition here. So the second thing we have to handle is the DC in the top. And that is the convection loss of hydrogen sulfide by convection to the bulk air, and this would be a Robin boundary condition. And here we have to use Fick's first law, which says that the flux is equal to the negative diffusion coefficient times the gradient concentration over space, like this. And if we use the mass transfer approach, the flux is equal to mass transfer coefficient times C, the concentration, minus the bulk air concentration, which is the driving force. So we can set these two equal to each other. And the next step is that we discretize dc dz. So we get so this is in the top boundary. So this is at position ni, and it will be ni plus 1, and at all radial positions this is central differences divided by 2 times dz, which is equal to Ka, and it would be Ni. And in this exercise, we will just set C air is equal to 0. So there's no hydrogen sulfide in the bulk air. However, because we are in the top and we also have a radial position, so far I've just showed you this column, which means all columns, but we actually still have diffusion along the r dimension. So you can imagine it that we are at this point up here. We are modeling the flux in this direction, but we still have some movement of particles due to diffusion in this direction. So we must not forget that. And therefore, we will make a loop where we calculate the derivative in each radial position. We will go from 0 to nj. Nj is the last index in the radial dimension, and the ghost point will be where we take this this equation and we isolate this point here, which is one point to the right, or to the above the top of the model domain. If we isolate this, we can call it C up. We will get the following equation. Now we will split the governing equation, which is, I can just show you how it will look. So the governing equation will look something like this when you have cylindrical coordinates. And we will split it up and calculate one of these terms at a time now. And remember, we are still only at the boundary, the top boundary where we are looping through. So first, this one. So yeah, so this is where we have to substitute the ghost point into the discretized form of the second derivative. And the discretized form looks like this. And here we would have ni plus 1, but that is outside the domain, and we substitute with this one, the ghost point that we isolated. Then for this part, just copy. Here we will have the discretization across j instead. So it will be j minus 1. And divided by dr squared. And then for the last term, which we have here, that will be central difference of the first derivative, which is just ni j plus 1 minus, and here it is divided by 2 times dr. And now we can finally put in the values in the time derivative, which is the governing equation. That would be the diffusion coefficient multiplied by all these terms. And for the last term here, it's actually 1 over the radius, no, the radial position, like this. Right, so that was one boundary condition, the upper one. Now we go to the third boundary condition, and that is on the left side, which is actually at the center of the tank in this case. So because we are at the center and we have symmetry, the gradient dc dr will be 0, and that is a Neumann boundary condition. So if we have the, again, Fick's law, we can actually derive that the discretized Fick's law here, which should be equal to 0 because we have symmetry, and we can then see that that this point here, which is 1 to the left of the left boundary, that must be equal to this one in order for us to get 0 in this whole term. So that is our ghost point. And we will later substitute that into the governing equation. But like for the other one, we will loop through all the points in the z dimension. So now we are working on this axis, and we will loop through all the points on this axis here on the boundary. So we will make another for loop. And first we will define the ghost point. We call it C lift. So that was actually just this one, which was equal to this one. And instead of having these indices, it should be like this. So it will be at I and then position 1. Then for the diffusion in the Z dimension, well, nothing special happens here except normal diffusion. So that is just a discretized form, and I will put that in directly here. So that is the discretized form of the second derivative, where we discretize across I here. So that is on the vertical axis. But for the radial dimension, we also have diffusion. And here we have to implement our ghost point. So let's write it down. So normally in this position we would have index ci minus 1, but minus 1 is outside of our domain, and we have made this ghost point to substitute it, and that is ci point 1. So it's actually two of these, but I will not write it out like that now. And divide it by the space step size squared. Then we also have dc dr, but because the gradient is 0 here, we just put it directly to 0 like this. So we can ignore it, but this is only the case when we are at the left boundary. When we go to the interior nodes, we will also calculate this one. And we can define the governing equation for the time derivative here. So that is, we are still on the left boundary. That is why we have index 0 here in the R dimension, and we're doing it along all the set nodes. So this will. So as you can see, we looped through from 1 to ni, but ni is exclusive. So we are not catching the upper left point